Hello and welcome. Following our first lesson on the purpose of the Millis function, we will now move on to a practical example demonstrating how to use it effectively. We will carry out this project using both the TinkerCAD simulation application and a physical setup. First, we'll design the circuit using TinkerCAD. We will control a 5mm red LED connected to pin 13 of the Arduino board using the Millis function. The circuit you see on the screen is also being assembled physically. We have set up our circuit physically and connected the USB cable to the Arduino board. Now, let's examine the commands step by step, analyzing each line in detail. In this first line, we define a constant named LED pin. This tells the Arduino which pin the LED is connected to. The value is set to 13, which corresponds to the built-in LED on most Arduino boards. And we will use this LED together with an external LED. Since this is a constant, its value won't change throughout the program. Integer LED state is low. Here, we declare a variable called LED state. It holds the current state of the LED, either on or off. Initially, it's set to low, meaning the LED is off. If you prefer, instead of using the low keyword, you can write the value as 0. Typically, integer-type variables store whole number values. However, since low in the Arduino IDE represents the value 0, we are essentially assigning the value 0 to the LED state variable. Unsigned long previous time is 0. This line creates a variable to store the last time the LED changed state. We use the unsigned long data type because it can hold large numbers, which are necessary for time calculations. At the start, we set it to 0 because no time has passed yet. Constant long LED duration is 100. Here, we define a constant for the duration of each LED state, how long the LED stays on or off. The value 100 represents 100 milliseconds, so the LED will blink very quickly. Now we enter the setup function, which runs once at the beginning of the program. Serial.begin starts the serial communication with a baud rate of 9600. We'll use this to send messages to the serial monitor for debugging and understanding how the program works. Pin mode LED pin output. Here we configure pin 13 as an output so it can control the LED. And in this way, we'll be able to supply power to our LED whenever we want and cut off the power whenever we choose. The loop function is where the magic happens. This part of the code runs over and over, controlling the LED. Unsigned long current time equals Millis. In this line, we call the Millis function to get the current time in milliseconds since the program started. We store this value in the current time variable to use in our calculations. Now, we begin writing the commands for the key part of our program, the most important control structure. We will define a condition using the if statement. If current time minus previous time is greater than or equal to LED duration. Here's the main logic of the program. We check whether the time that has passed since the last LED state change is greater than or equal to LED duration. If it is, it's time to toggle the LED state. If the LED is currently off, we turn it on by setting LED state to high. Otherwise, we turn the LED off by setting LED state to low. In other words, if the difference between the current time and the last state change time of the LED is greater than the LED time value we defined earlier, which is 100, the commands inside the if block will execute. Therefore, after 100 milliseconds have passed since the Arduino board was powered on, the commands inside if block will run, and here we will change the state of the LED. And in these commands, if the LED is on, we will ensure it is turned off. If the LED is off, we will ensure it is turned on. Next, we write digital write LED pin LED state. After the LED state variable takes the value of high or low, we use the digital write command to send the value of the LED state variable to pin 13, which is stored in the LED pin variable. This way, our LED turns on or off. So this line sends the new state of the LED to the actual pin. Then we will send a message to the serial monitor. We will show the current time, the previous time, and the time difference, giving us real-time feedback on how the program operates. Finally, we update previous time to the current time. To ensure the same operations continue at 100 millisecond intervals, we redesign the value of the previous time and assign the value of the current time to previous time. This is because we are matching the moment the LED state changes with the current time. Thus, when the current time increases by another 100 milliseconds, the condition in if block will run again and the LED state change will occur. This ensures that the program calculates the correct time difference during the next cycle. We use the Millis function to measure time without blocking the rest of the code, allowing for smooth and efficient operation. After verifying that every opening parenthesis has a corresponding closing parenthesis, we will ensure the code is uploaded to the board. First, we select the port to which the Arduino circuit is connected from the Tools menu. Then, from the Tools menu, I select Arduino Uno as the connected board. Now, the commands can be compiled and uploaded to the Arduino. Our commands have been successfully uploaded to the board. As you can see on the screen, our physical circuit is working correctly, and every 100 milliseconds, the LED state changes, causing it to blink on and off. We have tested our program. Now, let's monitor the data through the serial monitor. Again, from the Tools menu, we select Serial Monitor and check the data displayed on the screen. As you can see, the value of the current time variable is displayed on the screen based on the value returned by the Millis function. The value of the previous time variable also tracks each LED state check and is displayed accordingly. We can see that the difference between them is 100 milliseconds. Thus, we have verified our program by printing the data to the serial monitor. Next, we switch to the TinkerCAD simulation environment and run the same commands in the code section. We will start the simulation and test the circuit. As you can see, the LED blinks on and off every 100 milliseconds. Let's also check the program data through the serial monitor. The value of the current time variable is displayed on the screen based on the value returned by the Millis function. Similarly, the previous time variable, which tracks each LED state change, is also printed. And we can observe that the difference between them is 100 milliseconds. You can see the code for the same example written using both the delay and Millis functions. Using the delay command is much simpler, and the code is more concise compared to Millis. The purpose of your program will determine whether to use delay or Millis in a given situation. For instance, if your project requires continuous monitoring, such as constantly checking the state of a button, in that case, you may prefer the Millis function over delay. In our next lesson, we will work on a more comprehensive example using the Millis function. Until then, take care.